I'm really happy to be here for many different reasons. One of them being that I just checked the weather forecast for Toronto, where I'm from, and they're expecting a major snowstorm today. So I'm really happy to be here. So to provide a little bit of more general background, so my broad research interests are in system reliability, and what I do care about in particular is how do systems fail in the field. And the reason that I'm interested in that as a research area is that if you want to answer this question with information that's out there publicly available, it's very difficult. So you could, for example, follow the news. And then you see stories like the one of the man in Colorado, which you might have heard about, a man who was very frustrated with his computer, and he took it at night in a dark back alley, and he shot it 8 times, and the computer failed. So maybe that was a bit sensationalist, but if you read The Guardian, a Pulitzer Prize-winning newspaper, had a headline recently, "Millions are driven to attack their computers." So based on these, you could believe that millions of computers fail just because they are killed. But maybe that's not what's really happening. So you could look at a different source of information. So you could, for example, look at vendors' data sheets, which provide for each hardware component all kinds of specs, including some reliability specs. The problem is that the specs that vendors put out are specs that they put out to convince customers to buy their stuff. So maybe it's not the most objective source of information. So what I'm trying to do my work is work with companies, work with large-scale production systems, and get real field data for those systems. And in the past, so I've spent quite a bit of effort on that. I've gotten data from a bunch of companies, large companies like Google or Network Appliances, a major storage vendor, quite a few who prefer to remain anonymous. And then I've gotten a bunch of data also from national lab supercomputing sites, Scinet, for example, which is Canada's largest supercomputer, just because these guys have a lot of hardware sitting around, so they do see a lot of failures. And they're often more willing to share their data than companies are. So over the years, I've gotten a pretty broad collection of all kinds of different failures, things that can go wrong, ranging from things like hardware replacements. Yes?
From the last slide,
yes.
By the way?
Yes.
Have you also considered talking locally here to the Internet Archive?
Yes, that is actually a good idea, and I have not. Yeah.
You stick around Friday at lunch. They have an open lunch.
That's very important. My plane is leaving tomorrow at 7 a.m., but I'm in the area frequently. That's actually a good point. Yeah.
Email works.
Yeah, I mean, the problem is you need to have places that have a large amount of data and that are also very good at collecting and keeping data about failures and whatever else is happening. So and they're willing to share. So that narrows down the field quite a bit. So different types of failures that I have gotten data on are things like hardware replacements, a whole bunch of different error modes in storage systems, generally server outages. I've recently started to look also at job logs. Why do jobs in large-scale, massively distributed systems fail? And one thing that across all these different types of failures or errors that I've looked at that kind of struck me is that I was talking to all these people that provided data, the operators of those systems. I've talked to vendors who are often surprised about how their components behave in the field. I couldn't figure out, I mean, you have the people who make those systems and you have the people who run them. And a lot of the observations that I got were really surprising. And they were surprising even to those people, the operators and the manufacturers. And what that kind of tells you is that really in the field, reliability often looks very different from what you can get out of simple tests in the lab, where you take components, you put them under some accelerated live stress testing and see how they behave if you do that. So if you artificially age them, basically.
Maybe they don't want it.
Or maybe they don't want to. That's another. I didn't want to say that. You said that. This is being recorded.
I read between the lines.
They need to chip the systems.
No, it's possible, right? If you, yeah. So what I'm going to focus about today is one of very recent things that I've worked on. That is flash reliability. It's actually something that got published just yesterday at FAST. That's actually what brings me to town. So failures in solid-state drives is what I'll focus on for this talk. And you might ask, why flash? And the answer is pretty clear if you think about it. more and more data is living on flash. A lot of systems are now all flash, actually. The market share keeps increasing. So as more data is living on flash, obviously the reliability of our data depends on the reliability of the underlying flash. And then with flash in particular, there's always this general fear because flash is known to wear out. So what happens once you really use your flash? What happens to reliability once the device wear out? And the motivation for flash in particular was also that for flash, it's a relatively new technology that's studied really, really well in the lab. And pretty much all our knowledge that we have comes from those lab studies. Now, flash has been used in the field for long enough that there is actually field data available. So we're just now at the point where you can actually say interesting things about what's happening in the field. Unfortunately, right now, there's only one other field study that was published by people from Facebook last year. So our goal was basically get a much broader and deeper understanding of how does flash fail in the field, how reliable or unreliable is flash. So the data that we used, so this is work that I was doing while I was on sabbatical. I spent 4 months of my sabbatical at Google. So the data that we used was collected across Google's fleet. It's a really nice data set. So first of all, because it does span all of Google's fleet, it covers 6 years of data. It includes more than 10 drive models. What is really nice from an analytical or measurement point of view, if you analyze this data, is that these drives are actually custom drives. So the chips are commodity flash chips that everyone can buy. But then Google developed their own FTL and their own ECC. And for all the models that I'll include in this talk, the ECC and the FTL is the same across models. And what it means is basically if we compare different models, we know for sure that differences we see are due to difference in the underlying flash and not due to differences because the ECC was different or the FTL was different. So it makes meaningful comparisons possible. So the chips come from 4 different chip vendors. They include all the common types of flash, MLC, SLC, eMLC. And there is a lot of data on what these drives actually experienced while they were in the field. So there's data on repair events, replacement events, bad chips, bad blocks, but also all kinds of different types of errors and information about the workload that these drives have experienced. So it's a very rich data set. Google is one of those companies that's really good about collecting data for all the systems and keeping this data also. They don't just keep the last few months so that their admins can use it for troubleshooting or whatever. You can go back to, say, 2004 or whenever they started data collection, they have it all. They might have to go to tape and get it online for you, but it's all there. So for doing measurement studies like this is pretty perfect. Okay, so it's a lot of data, and it's a relatively short talk in comparison. So I'll focus on some of the key results, but I'm happy to take any questions on other things, or you're, of course, always welcome to read the FAST paper if you want to know all the details. So we started with a very high-level question, and that is, once those drives go in production, they're deployed in the field, what is their lifetime? So how long do they last before they get replaced due to suspected hardware failures? So what's the replacement rate, the annual replacement rate for each year? What percentage of drives per year do you expect to get replaced? And that's what this graph here shows you for all the models that we had a significant amount of data. So what you observe is replacement rates, yearly replacement rates of, say, 1 to maybe 2.5%. And you might wonder, is that a lot or is that a little? So to provide some perspective, one thing that you could do is look at hard disk drives. There's, in the meantime, been quite a bit of data published on hard disk drive failing in the field. And you see a very broad range, ranging from 2% to up to 20%. Backblaze, one of the companies in the Bay Area, made actually some data publicly available that you might have seen. So the averages are probably in the range of 4 to 5%. So that's good news. So in terms of replacement rates that you see for flash, it's actually a lot lower than hard disk drives. And one of the reasons that might have helped these particular drives in this population is that Google built in a mechanism that allows drives to tolerate a certain number of chip failures. So when a chip fails, it doesn't mean that the drive is bad. It means the system will just ignore this chip, map it out, and the drive will continue to operate with reduced capacity. And some commodity drives do that. They do that by putting in spare chips. So it's something that happens in commodity drives, but not all of them. So about 1% of all drives see per year in the field a chip failing. So these extra 1% would have had to be replaced if they didn't have this mechanism for tolerating chip failures. So that was the high-level view. That yes, yes, sure.
The A, B, C, and D represent chip manufacturers. So the eMLC is the same as the
They represent different models.
Yeah, I understand.
And the different models are different in the type of flash they use. Some of them are from the same vendors. So A, B, C, D are not all from different vendors. And we looked at the effect of vendors, and I've seen the same for hard disk drives and the same for DRAM. It's not always one vendor being better than the others. Each of them has some bad models and some good models, and it's not as easy as saying, okay, I'll only buy vendor X and I'll be fine. Yeah. So what we wanted to figure out, so that's just a high-level picture. How long do these things last before we have to take them out and replace them by something else? What we also wanted to look at, while these drives are in the field, how do they behave? What kind of errors do they experience? And these drives, because they're custom drives, have very detailed error reporting. So you're not stuck with the standard smart interfaces that commodity drives have, where you often also don't know how to interpret it. So they have a lot of different types of errors. And at a high level, you can group them into two different categories. So they're transparent errors. These are errors that the drive can hide internally, mask them, so they will never be visible outside of the drive. And then the non-transparent errors that maybe the drive tries, but it's not able to mask them. So it will have to return back an error to the application higher up. So transparent errors would be something like correctable errors. So you have a bunch of bits flipped, but there's drive internal ECC, and you can correct those flipped bits, and you can deliver the data that's being requested. There's read and write retry errors. So these are situations where a read or a write leads to an error, but the drive retries internally and eventually it succeeds. So that doesn't become visible to the application, the operation still succeeds. And then there's an erase error. Erase error means a block cannot be erased. The drive tries to erase a block and it can. This means this block is probably bad and cannot be used anymore, but it's not critical to the application. So for non-transparent errors, one type are uncorrectable errors. So you have too many bits flipped. The ECC cannot handle it, cannot correct it. So at that point, you cannot read the data that the application is requesting you to read. There's a final write error, which means a write led to an error. And even after retrying many, many times, you can still not write the data that the application asks you to write. There are metadata errors, which means the drive cannot access drive internal metadata. And there are timeout errors, which means the drive just fails to respond in a timely manner. And there's a timeout. So our question was, out of all these different types of errors, how frequent are they? So what percentage of drives in their lifetime sees at least one of any of these types of errors? And this is a graph that shows you the results for one particular drive model, but it's somewhat representative for most drives. So what you see, first of all, if you look at the top bar, and that's maybe not so surprising, pretty much all drives, nearly 100%, see correctable errors. So there's a reason why these drives have ECC, otherwise they would have errors all over the place. What is maybe more interesting is if you look at the second most common type of error that affects, depending on which drive model you look at, between a quarter to more than half of all drives are uncorrectable errors. So these are situations where the application is trying to read data and the drive cannot deliver it because there were so many bits corrupted that it couldn't correct the corruptions and it has no idea what the data is that you're asking it for, what was stored there.
This is before error correction.
The uncorrectable ones are after error correction. So you try everything you can with the ECC that you've stored, and you can still not correct it. So the correctable ones are the ones that after ECC, they go away. So they are there, but you don't care really.
How do you detect the correctable errors? Are they logs?
Yes, exactly. So these drives have so they're custom drives, so Google has basic control on what errors are reported, and they collect data on all these different types of errors. So for each day, it's aggregate data, so for each day, I know how many, for a particular drive, how many errors of each of these types have been observed. Yeah.
You know, if the drives have end-to-end data protection, that it means that they cover also the data?
So I don't know that for sure. I probably wouldn't be allowed to tell you if I knew, but I would suspect that this being Google, Google tends to do things end-to-end from the application down to the hardware. So I would be pretty sure that they rely on higher levels, say the file system level, to put in those checksums if there are problems that either the drive has missed, or there might be errors that are not at the low flash chip level, right, but that happen higher up in the stack to protect against those.
Is the FTL open enough such that you could have designed your ECC in a way that those uncorrectable errors go away? Or
that's always the problem, right? You can probably, for any flash drive that you design, you could always make the ECC insanely strong and have almost no errors, but then you have the problem that it takes more time to compute the ECC, you need more space, exactly performance space, there are all the other overheads. So that's...
Whoever built the ECC, this was the perfect trade-off of failure rate or uncorrectable errors.
So in general,
lost capacity.
In general, one of the reasons that they probably do their custom drives is because then they can decide what is for them the perfect trade-off between the error rates that they see and the overhead that this particular ECC strength costs them. That said, though, I think it's very difficult, and I'll talk about that a little bit later in the talk, to decide, because you have to, before you put these things into production large scale, you have to decide what's your ECC scheme, right? And so you're kind of stuck with doing lab tests, and for that, trying to figure out what ECC strength will I probably need. And that's not such an easy question, as I'll show you. Yeah?
What kind of bit error rates are we talking about?
So all I can tell you is that these are, so the particular chips that I'm looking at here were chips that were put in production in 2006. Their lithography it ranges from around 40 to 50 nanometers, so it's relatively large compared to chips now. I can't tell you any more details than that.
They are not using linear prediction.
What's that?
They are not using linear prediction correction.
So what they exactly used for their decision making and designing the FDL, I don't know, because I wasn't involved in the process. But I show you one standard way that people use in lots of research papers, and that I think might not be the best way. Yeah. Any more questions? Yeah, so going back to these uncorrectable error rates, you might ask, so this does look high, and if you compare that to hard disk drives, we've seen before that flash drives have, in terms of replacement rates, they have a big edge over hard disk drives. But if you look at sector error rates in hard disk drives, published papers typically talk about 3 to 4% of disk drives seeing in their lifetime sector errors. So that's much lower. And to some degree, of course, that is a design choice, again, that disk manufacturers figured that's what they have to do to keep the customers happy. And there was actually yesterday at FAST, there was a keynote by Eric Brewer from Google who was actually arguing that Google would prefer if these hard disk drives had higher error rate, if that means they can get them cheaper or higher capacity or whatever. So it depends on what your particular needs are.
You're saying they work around those?
They work around those, and probably most...
They would make more money by having more fault, their own fault detection.
Yes, I mean, I guess if you now look at a lot of data centers and how they are run, right? The same is the case for Facebook or Amazon. There's so many layers of redundancy at the higher system levels. So if you anyways have 3 copies of everything, why does the hard disk have to be like 100% reliable, right? You can deal with some errors. So that's true. Yeah, so these error rates are pretty high, and they're actually similar. So this is not necessarily a Google-specific thing. Those are actually in similar ranges as what the Facebook paper has reported. So it's not something where Google is doing something insanely different. Mm-hmm.
So these have 100% ECC. So every single, all the flash memory is protected, or are some of it not protected?
So you mean are different parts of the flash protected with different strength of ECC?
Yeah.
For one generation of models, all the flash chips, all the flash on one drive always use the same ECC. Over different generations, the ECC changed. So all the drives I'm talking about here are the first generation that have one strength of ECC. And there's a second and a third generation of drives that have different ECCs. And I can't tell you the strength of the ECC, and I can't tell you anything about the details of the FDL. So that's one of the things that Google considers part of their IP. And yeah, some of the trade-offs you have to make if you want to get data.
So other than ECC, where leveling is another factor. So how does that play into
the FTL? Yeah. I mean, it's another design decision that you make when you design your FTL, right? Where living is a critical part. And all I can say is that
also mismatch of the where leveling versus your data pattern, data usage, right? How frequent you write to.
Right, but you wear some parts faster than others if you don't wear level perfectly. Yeah, the FTL is proprietary and we can't share it. What I would say is, if this was just because of stupid wear leveling in the FTL, these drives were used for quite some time. So if that were the problem, probably they would have changed the FTL and just upgraded it, right? Updated it throughout their fleet. So it's not very likely that there were some very obvious bugs or inefficiencies that wouldn't have been fixed over such a long time period. So just in case you're wondering, the other error types that are relatively common, like read retry, write retry, or final write errors, those are typically considered symptoms of bad blocks or bad chips, and there's more detail about that in the paper. What I'll focus on in the talk is uncorrectable errors, correctable errors, because that seems to be the dominating problem if you look at flash reliability in the field. So what we did want to know after seeing those error rates is, what are the factors in the field that affect flash reliability? So which one of the various things that people talk about when they talk about what affects flash is really a problem in the field? So the obvious contender there is wear out. As the number of program erase cycles increases, everybody believes flash reliability goes down. There's a question of technology, eMLC versus SLC, lithography, age, and workload. And I look at all of these. So the question is, when you look at reliability, what metrics should you use? And one metric that I'm using is a very widely used standard metric, RBER. RBER basically means raw bit error rate, and it means the number of errors, the number of corrupted bits that you're seeing, divided by the number of bits that have been read. So for all these drives, I had information on the number of corrupted bits, and I knew how many reads happened. And remember, these are production workloads, so whatever, how many reads there were depends on whatever the workloads were that were running on these systems. So I didn't have control over that. The second metric is the probability of seeing an uncorrectable error within a certain time period. And you might wonder, if you've looked at flash reliability, why I'm using the probability of seeing an error rather than looking at things like UBER, the uncorrected bit error rate, which is more common or traditional. And we'll see in the talk why I'm not using that. So from now, trust me that it's a good idea to look at probabilities. So starting with factor number one, the effect of wear out as a function of program erase cycles. So that's one thing where actually all the previous work that looks at accelerated live testing in the lab agrees. As P cycles increase, RBER grows exponentially as a function of P cycles. So what we wanted to know is, how does this function look like for the drives that we have data on? That's what this graph here shows you. For those models where we had data for a large P cycle range, shows you for each model the RBER as a function of the P cycles. And if you look at that graph, you make two observations. One is that, first of all, there's big differences between the different models. And we'll talk about why that might be the case. The other interesting observation is that really there is increase, clearly, but it looks much more linear than exponential. And we verified that with curve fitting. It's quite obvious just by looking at it. So that's clearly different from what people had expected. Another thing that's very interesting, because people always have this angst, what will happen if a drive crosses or exceeds the number of PE cycles that the vendor specifies is the maximum number that this drive can tolerate? Will all my drive at the same time fall over a cliff once they reach this limit? So if you look at these drives, for almost all of them, the PE cycle limit was 3,000. And as you can see, for those drives where we had data past it, even past this limit, there's no sudden jump or anything crazy happening. The increase continues, but it continues at a linear pace.
Did you try any much longer?
So that is a good question, right? What would happen if they had been used for longer? And unfortunately, I don't know that because I'm stuck with measurement data, and there were not enough drives that made it past this point. But it's a good question.
Because people use mechanical strain and stress.
Yes.
Chips,
so what I did try to do is I went back afterwards, after we did all the studies, and I asked the group at Google who did, during the procurement phase, all the tests on the drives before they decided what to purchase. So for them, some of these drives did get the data from the tests. And in those tests, they did see an exponential increase. And they did eventually also see a very sharp increase, but that didn't happen until 2 or 3 times the PE cycle limit. So what that tells you is that vendors are probably very conservative about choosing this PE cycle limit. Exactly.
Yeah, because one thing that you're missing in this, and so typically in LLM models, you don't just care about number of programming cycles, but also the time between programming cycles.
Yes.
There's an opportunity for relaxation to happen.
Yes, and that, yeah, so to some degree I can look at that, but not in a lot of detail. And the problem is that the data I have is daily aggregates. So I cannot really say exactly how much time there was in between. I can look at averages only. Yeah.
Was the 3000 P cycles consistent across all the vendors? Because usually SLC tends to have a lot.
Exactly, yes, and I'll talk about SLC in a second. So that was the case only for the eMLC drives on top. So the SLC drives had 100,000 cycles. So they.
For eMLC, all technologies, eMLC used to be 10,000 cycles. So there are differences across vendors.
It is of course model specific. It's just for these models, I guess, because they were all put in the field at the same time. They probably had similar, although it's different vendors, they had similar technology and they had all a 3000 P cycle limit. So what's interesting now is this was just for RBER. What happens if we look at our uncorrectable errors? And you see actually very similar behavior. So this plots as a function of P cycles the daily probability that a drive will see an uncorrectable error. So very similar increase, but it's linear. And again, no sudden disasters that happen once you reach the P cycle limit. The turquoise one, right? Yeah, the problem is because it's only one single data point, and that's where the data ended, I can't say whether that was an outlier or whether that's a trend. Because there are lots of other things, so you have, and that was one of the reasons actually for looking at probabilities. They're more robust than if you look at rate, especially mean rates. But it could also be, I see spikes also in other graphs for much lower P cycles. It could be that it just happened that one data center, for example, had a power outage. And as a result, all these drives happen to have some issues with their reliability. So it can be all kinds of other factors that I cannot account for. So it's true for this one data point. But yeah.
Especially because it's SLC, that's what makes it very equational.
The bottom two ones are SLCs, yeah. So they are very predictable, but they're also very far from the end of their life in terms of P cycles. And that's actually a good next question. What is the effect of SLC versus MLC? I mean, generally, SLC drives, for those of you who are not familiar with the details of flash technology, are the much more expensive drives. And the reason is that in a single flash cell, you store only 1 bit rather than multiple bits. And that means that it's maybe easier that bits do get corrupted. It also means that they're more expensive because you get less capacity out of a drive. So what is the difference? Going back to the picture that we looked at, and I've already given it away before. So the two red lines are actually the SLC drives. So for RBER, it's very clear that these drives give you better RBER rates. And that's kind of what you would expect. So more interesting is if you look at uncorrectable errors. So if you look at uncorrectable errors, you see that actually the worst model in the whole data aggregation, that one that takes off pretty steeply at 500 P cycles, was actually an SLC drive. And there are two other SLC models that I don't have included in this slide because they didn't cover a large enough range of P cycles. But out of those two other SLC models, one was also consistently worse than the eMLC drives, and one was better. So basically, it seems when you care about uncorrectable errors, the difference that SLC makes is not as predictable as when you look at RBER, where it's very clear. And again, so all these drives use the same ACC. It's not because there was different ACC for different models. This is all due to the underlying flash rate.
Is that because there were early chips in the learning curve or something?
I don't know. I wouldn't, 5, 6 years ago, I wouldn't call that very early in the life cycle of flash products. And if anything, I would actually expect that based on the data I've seen for later generations of flash drives at Google, that I didn't include in the paper because there wasn't a large enough sample size. They are younger drives. These things have gotten worse, although the ECC has gotten stronger. the error rates have actually gotten worse.
Because of the shrinkage of the
Because of lithography, exactly, yeah.
Is there any analysis done, say the electron microscope, whatever? For instance, people with lithium batteries do that all the time.
I'm sure somebody has done that. For this data, it's field data, so I have no idea. So nobody for those. So for example, for this model that is so terrible, the red one that takes off. I'm not sure whether anyone at Google has ever looked into, or whether they talk to the manufacturer about what is happening. I mean, it happens, these kind of things happen a lot also in the hard disk world. If you look at the data from Backblaze, for example, there are some hard disks that stay always at like 1-2% failure rates, and there's some that in the second year suddenly jump to 10% or 20%, which is terrible. And there are some models that turn out to be bad once they're in the field. And if we could predict that beforehand, it would be great, but it shows you that it's not that easy.
Were you talking to at Google?
So I was working with the storage analytics group. So that's the group that hosted me. But I did a lot of this work in collaboration with the group that was actually developing the FTL, the SEC, and all that. So the more hardware-oriented people, hardware platforms.
Yeah, another person to talk to there is Urs Holzel.
Yes, and then
Urs is a good person to talk to.
I'm sure he has seen a draft of the paper, because before you publish anything, this has to go up pretty high, and everybody has to sign off. And I'm sure he has signed off. I haven't had a chance to talk to him in person, yeah. So this is error rates. I did actually also compare what happens if you look at rates of repair or replacement, and compared SLC and MLC. And again, SLC drives didn't look any better than the MLC drives, which is kind of unexpected. So someone here pointed out lithography, and that it clearly has an effect. So that's one of the other things we looked at. As feature sizes shrink, density increases, you expect that error rates are probably going up. So the drives in this study do actually have different lithographies. So looking at RBER rates here first, if you focus on the red ones, the SLC drives, the one that is worse happens to actually also be the one that has smaller lithography, 34 versus 50 nanometers. And if you look at the MLC drives, the blue one, which is clearly worse than the others, is the only one that had a 43 versus a 50 nanometer lithography. So clearly lithography, as you would expect, does impact RBER. Let's see what it does to uncorrectable errors. So if you move to the uncorrectable error slide, so actually those two models, the red triangled line and the blue line, that are in their class, the ones with the smallest lithography, are actually not significantly worse than the other drives in their class at all. So it seems that for uncorrectable errors, lithography might have an effect, but it doesn't seem to be the dominating effect that gets your uncorrectable errors up or down. So one thing that we wondered about is devices age. For flash, there's a lot of focus on wear out due to P cycles growing over time. But we wanted to know, is there maybe also wear out just because a drive has been in production for a long time and it has been in use, even if it didn't have a very high number of P cycles? So we looked at what is the correlation between age, measured just by number of months that the drive was in the field, and RBER. And this is the Spearman correlation coefficient that we got for the different disk models for age on the right side here. And as you can see, they are clearly very high. Everything above 0.1, 0.2, you would consider a clear correlation. But the problem, of course, is that there's a clear correlation with P cycle as well. And if a drive is older, it probably has seen more P cycles. So we did actually a lot of work separating out these factors. We did it in different ways. One way that's the easiest to present it visually is we took all the data points that we had, and we divided those data points in two groups. So I take all the drive days that I have, and I look at those drive days that were for older drives that had been in the field for longer at that time. And I make a separate group of data points that are for younger drives that have not been in the field for very long at that time. And then I plot their RBER separately against P cycles. And what you see if you do that is that the older drives are clearly worse than the younger drives across the whole P cycle spectrum. So that basically tells you that independently of P cycles, just being in the field for a longer time increases your RBER. So age has an effect beyond just P cycle-induced wear out. Yes?
Would the age of the drive also possibly affect, like, be impactful, like its design?
Like what does that mean?
So these are, and that's actually, it's a good question because I should have made it more clear. So all the drives that are included in this plot on the right are drives from the same model. So they have the same FDL, the same ECC, and everything. So just different data points. So there are some drives that reach 3,000 PE cycles in, say, 1 year, and there are others that don't reach 3,000 PE cycles until they're 3 years old. So you can compare a 1-year-old drive with 3,000 PE cycles with a 3-year-old drive that has 3,000 PE cycles. And that's how we did the comparison. But we also did statistical analysis, and you can show the effect of age independent of PE cycles.
1,500.
That's exactly what, that was one of the things that I meant that I was talking about when somebody was asking in a previous graph about the spike in the end. You sometimes see those spikes, and unfortunately it's pretty much impossible to say exactly what has happened, because I can go back in time and look at the data, but the only information I have is what the data tells me. And it could be anything. Maybe around that time in one data center, there was a failure of the cooling system and rates went up, or there was a power outage, and after that the hardware was more flaky. And it's really for these very high rates, sometimes it can be one data center that kind of biases the sample. So it's difficult to say.
You know about the bathtub model?
Yeah, of course.
So is that consistent with that the older drives are on the
slow
up
I
again?
did try to map it to the bathtub model as well, actually. And so that's essentially what the bathtub tells you. You cannot do the bathtub right away, because you will see a bathtub just because as drives get older, they have more PE cycles. So it is aging because of program array cycle wear, or not just aging by itself. I looked at infant mortality, and it was very minimal. But that might just mean that the
outlier was not an infant?
No, he was not an infant, because the outlier also made it to 1,000 PE cycles. So
Stochastic aspect.
it could be in the first month. Yeah, that's true. That's true. It doesn't tell you anything about time.
Variance.
That's
Children's sickness has
that's
higher
true.
variance.
And these are the younger drives also. Yeah. I didn't look at it for this specific case. I looked at infant mortality in general, and I saw very, very little the first few weeks maybe. And that might not mean, it probably doesn't mean that there is no infant mortality. It might just mean that the testing that they do, the burn-in testing before they put the device in the field, is good enough that you can remove the infant mortality cases.
Well, I just would argue that the bathtub model is a mean. Then there's a variance on that they usually don't model. I think the variance on the infant is probably higher than on the...
That is probably very true, right? Because you might have some very bad cases that in the beginning get the curve up. True, yeah.
You mentioned that lithography didn't have an effect on uncorrectable errors.
So I can't say that it has no impact. What I can only say is that it doesn't seem to be a dominating factor, because those drives, so in each class, the eMLC and SLC class, the ones with the smallest lithography are not the ones with the worst uncorrectable error rates.
And is it possible that they have stronger ECC?
No, all these drives, they all have the same ECC. I know that, yes. Okay. That's a nice thing about this data that you don't get if you do a study based on commodity drives. You have no idea for each of the drives what the FTL does internally, what the ECC does internally. So this here tells you really that the differences must be due to the underlying flash, because everything else is the same.
But they might have different data organization or wear leveling or...
So the wear leveling is the same. It's really it's exactly the same code, yes.
How about the internal chip ECC?
That, of course,
Google's
can be different.
ECC.
Exactly. So
right.
that can, of course, be different. That's true. Yeah. Yeah. So I shouldn't say it's the underlying flash. It's the flash chip specific. Yeah. That's more correct. So age does seem to have an effect besides just wear out. So one common concern that people also have frequently is the effect of workload. And there have been lots of lab studies that have demonstrated different types of workload-induced error modes. And those include, for example, read and program disturb errors, where basically reads or writes disturb neighboring cells, or incomplete erase operations, where a block is not completely erased. And all these can affect your error rates. So the question is, how dominant are these error modes in the field? Is this what affects your RBER? So what we did to answer that question is, we looked at, in a given month, is the RBER that we see in that month correlated with the number of reads, number of writes, or the number of erase cycles that we see? And when we did that, we saw for at least 2 models a pretty clear correlation for each of these, reads, writes, and erases. Now that's tricky, so correlation doesn't mean causation, because all these three are also correlated with PE cycles. So we did more detailed analysis where we separated those effects. And what we see is that for writes and erases, the correlation goes away if you control for PE cycles. For reads, for at least 2 models, it still stays. So there are 2 models where read disturb in the field is an issue. And that's something the Facebook paper for their workloads concluded read disturb in the field does not affect error rates, but that might be model specific because we observe this for 2 models and not for the others. So what about uncorrectable errors? We did exactly the same analysis for uncorrectable errors, and turns out uncorrectable errors are not correlated at all with either reads or writes or erases. So the number of uncorrectable errors in a month is not correlated with the number of reads, writes, erases. The probability of uncorrectable errors is not correlated with any of these. So these error modes don't seem to affect uncorrectable errors in a significant way. That's one thing that this means. But it means one other thing, and I mentioned before that I'm not looking at Uber, I'm looking only at probabilities of uncorrectable errors, or what fraction of drive days had uncorrectable errors. And the reason is, if you do something like rates, where you say, I report errors as, so the number of uncorrectable errors, the number of corrupted bits, divided by the number of bits that I read, there's an assumption that the number of uncorrectable corrupted bits should be normalized by the number of reads. But if there's no correlation between the two, it doesn't make sense to normalize, because it would just mean that if you have a drive that sees a lot of reads and a drive that sees very few reads, the drive that sees a lot of reads will look much better in Uber just because we happen to normalize by this huge number of reads. So if these 2 quantities are independent, it doesn't make sense. It maybe makes sense in lab tests where for all the tests you always run exactly the same number of reads and then you normalize everything by the same constant. But in our case, Uber would really distort the results. So now comes the question that's always the frustrating question for anyone doing measurement studies. There are a lot of other factors that could potentially affect flash reliability that we have no data on. So for example, I didn't have a chance to look at environmental data like temperature, humidity, maybe patterns in the workload rather than just intensity of workload. So I can't say anything about those factors, but I did try to get an idea of whether there are factors that have a big impact. And the way I did that is I looked at all the drives for one model, and those drives from this model were deployed in different clusters. And what I saw is when I plotted the population in each cluster separately against PE cycles, that there's quite a bit of a difference in the RBER rates for the same drive model deployed in different clusters. So what that tells me is with the data I have, all these drives look pretty much the same. So I know they are the same model. I know I'm controlling for PE cycles. So there must be some factors that are cluster specific. It could be workload, could be environment conditions, could be many things that unfortunately don't know. But I can say that there are some other factors at play that we can quantify.
I think if you look at the JEDEC models for bit error rate, for flash bit error rate, most of them actually understand that program error cycles is not the only factor. In fact, as I mentioned, like the rotation time between cycles is very, very important.
Yes.
And if so if you're not looking at that, you're hiding that effect.
Yes, and that's why I try to look at a few things. So I try to look at because the problem when you look at field data, there's no way that you can ask people to log individual read or write operations or erase operations, right? Because the overhead would just be huge. So the only thing you can have is these aggregate counts. So I looked at some workload specific factors, like I tried to look at the read-write ratio. And that was actually different for some of the clusters. And for some models, it seemed when there was a difference like this, that could maybe be a factor. But again, I don't have fine-grained enough data that I could really drill down. Okay, so the next one is a more, so stepping back from specific factors and what impacts flash reliability. This is more a general philosophical question, that is, so what's the whole point of RBER actually? If you think about why people care about RBER, they really use RBER because it's a metric for overall drive reliability, right? So people use it in papers always in a way that's something similar to this paper, which is being cited all over the place, where you have your raw bit error rate and you say for a particular raw bit error rate, and as a function of what ECC I use, what strength of ECC, I assume this rate of uncorrectable errors. And I think one of the reasons is that, so first of all, RBER is much easier to measure in the lab than uncorrectable errors because you see correctable errors all the time, so you can measure them relatively easily. And it allows you to make predictions for different design choices that you might make, like different ECC strengths just based on one experiment, right? So what we wanted to know is how well does RBER actually predict uncorrectable errors? And the motivation, maybe based on the previous slide, is somewhat clear. There are a lot of factors that affect RBER and uncorrectable errors very differently. So we started by looking at the different disk models, drive models that we had. And we looked at, for each drive model, what was the median RBER for this drive model, and plotted that against the fraction of the drive days for this model that had uncorrectable errors. And if you look at this graph, it doesn't take a lot of time to figure out that there's really no correlation whatsoever. And we verified that statistically. So for drive models with higher RBER, there's no higher frequency of uncorrectable errors. But that's a pretty coarse-grained view looking at drive models as a whole, right? So we thought maybe what you should do is you should take for one drive model all the individual drives and look for all the individual drive, for each drive, what was the RBER and what was the fraction of drive days with uncorrectable errors. And that's the whole population for one particular model. So again, you see no correlation whatsoever. And you can show this statistically if you don't trust your eyes. We also looked at even finer grained data. We looked at within individual drives. What if you look at individual drive days and you check, do drive days with higher RBER have a higher probability of seeing uncorrectable errors? And again, there was no correlation whatsoever. So what that basically means is that RBER is really not a very good predictor of those errors that you care most about, the non-transparent errors, and not very good predictors of field reliability. What it also maybe means is that, because how do you explain this, right? Why do these things look so different? So what it might mean is that the mechanisms that cause RBER are just different from the mechanisms that cause uncorrectable errors. So maybe, and I'm not an electrical engineer or a device expert, but what could happen, for example, is that you have retention errors where slowly over time bits get corrupted, and that feeds into your RBER. And then maybe in order to get uncorrectable errors, these errors maybe don't happen because just randomly, accidentally, you got unlucky and too many bits in your ECC chunk happen to be flipped. Maybe it's because there is something more serious wrong with the hardware. Maybe there's a chip that is marginal and where parts of it are failing, and that's what really causes your uncorrectable errors. But that's just one.
I think your conclusion is correct because, when you look at raw bit errors, like typically the single errors that are caused by one mechanism.
Yes.
If you look at uncorrectable errors, they're typically multi-bits or entire periphery went down or something. It's a different mechanism.
Right, and that's exactly my problem was that I didn't have location information. So I wish I had known for each correctable or uncorrectable error where exactly it happened, which chip, which block, and where on that block, right? But all I have is these aggregate counts. And I had a very similar situation when I was analyzing DRAM errors in the past, where it was the same thing, and I had a similar conclusion. Then Google did actually change your measurement infrastructure and added basically sample logging of all the addresses that had errors. And then you could actually see it's the same addresses that are repeating. And it might be something similar here.
Something you also have no control over, but sometimes you find data-dependent pattern sensitivity.
That is very, very possible. And that could be that depending on how, in which order you exercise things. And that's something that would be much harder to log, though. Because once you log workloads, then,
it happens.
Yeah. So this might make you wonder, what is actually predictive of uncorrectable errors? So RBER is not very predictive. A bunch of other factors don't seem to impact uncorrectable errors the way we think. So one thing we thought, and that was going back to this hypothesis that I have, that maybe it's something else that's really wrong. The hardware is marginal, something that's wrong with the underlying hardware. So what we did look at is is there maybe a correlation between other types of errors or previous errors that you have seen in a drive and later uncorrectable errors? So what we looked at is, we looked at an average month for one particular disk model. So we looked at all the drive months that we had. And we looked at, for an average month, so what is the probability that in an average month you see an uncorrectable error? And that's that tiny little bar on your right there. And then we looked at what is the probability of seeing an uncorrectable error within 1 month after seeing any one of these previous types of errors. And that is the green bar. The yellow bar basically says what's the probability of seeing an uncorrectable error in a month if at some point, any point in the past, you have seen any one of those previous types of errors. And what you see, and that is kind of interesting, pretty much any type of previous error, any one of these different error types that the drives log, have some correlation with later uncorrectable errors. So in some way, that's positive news because it tells you there's at least something that has some predictive power about what are your chances of seeing uncorrectable errors. And one thing that I'm looking at right now is can you use machine learning techniques, for example, and based on everything that you know about a drive, say the age, the P cycles, previous errors, transparent or non-transparent, and predict what the chance of uncorrectable errors is. And we're playing around with this right now. So these are false positive against false negative rates for different models, and just a simple card model. We've refined that since then. And depending on what you want to use these predictions for, right? So it varies what false positive rates is acceptable to you. What this graph says is that, for example, if you want to keep your false positives below 0.5%, you can still catch around 30% of all errors, which is not all of them, but catching a third of them is better than catching none of them. And we're right now looking at, so how good can you make these predictions? And if you can predict things, what do you do with that afterwards? So this was some of the findings in our paper. So we looked at a lot of other things. We, for example, went back and we looked at the tests that Google was doing in their lab before putting the drives in the field and the arbor they were observing in those tests. How close were those actually to the arbor observed in the field? And they were often quite a bit off. We looked at, in detail, how do bad blocks develop? How do bad chips develop? For bad blocks, one thing that was pretty interesting is that if you look at the number of bad blocks on a drive as they develop in the field, you either see a very small number, 2, 3, and once you pass a certain threshold, for a lot of drives it was around 5, then they develop massively. So basically, once you have more than 3, 4 handful, you're very likely to have a chip failure, because that's what it means. If you have massive number of blocks failing, it's probably a whole chip that's bad. We also looked at some things like all drives pretty much come with factory bad blocks that are bad from the beginning. And how many factory bad blocks a drive has, to some degree, is actually also correlated with the later behavior that this drive sees in the field. So we looked at more detail at bad chips. We looked at repair and replacement rates. It's all stuff that you can find in the paper if you want to know more. But for now, I'll just summarize. So some of the key points basically were, there's a significant rate of non-transparent errors, uncorrectable errors. So Flash looks good for replacement rates, but it does not look very good for those uncorrectable errors. They are to some degree predictable. That is the good news. What it also means, though, is right now all the file systems, everything, storage systems, they have been developed with hard disks in mind. And if you move to all flash, and I haven't even taken into account that these are relatively old flash chips with larger lithography, so as we move forward and densities increase, those error rates are probably not going down, they're more likely to go up. That's maybe something that as a storage system or file system developer, you want to take into account and make sure that you protect against those problems. And then that's something that I've found pretty much for all the different types of failures I've looked at. What you find in the field is really very often different from expectations that people have just based on previous assumptions. Often it's just anecdotes or actual lab tests. So for example, that there was this linear rather than exponential increase with P cycles, that arbor really doesn't translate very well to what happens to uncorrectable errors, that SLC, when it comes to uncorrectable errors, is really not much better than MLC. And then, yeah, there's quite a few other things that I have in the paper that you are welcome to read if you want to. It's public since yesterday, I think. So I'm happy to take any more questions if you have.
Did they provide you with any information about the environmental temperature for the drives?
So this data does exist, and it would have been really interesting to look at. I had only 4 months that I spent there, so I didn't get it. And if you are interested in temperature, that's something that the Facebook paper actually did look at. So the Facebook paper was in some ways a little bit more narrow because they used commodity drives, so they didn't have all this detailed reporting. They knew uncorrectable errors, they didn't know anything about RBER or other types of errors, and their drives are relatively young, but they have other factors that I didn't have information about, such as temperature. Yeah. And there was another talk actually at FAST yesterday that talked about it, but also in context of hard disks, not flash, that actually looked at free cool data centers, and they found that rather than temperature, humidity was actually a much bigger contributor to hard disk failures.
That's interesting.
Your initial slide had non-Google sources of data.
Yes.
And most of the talk didn't seem to mention the other stuff.
So for the flash data, all the data I have is Google. So the other data was for all kinds of other things that I have looked at in my life. So I have looked at lots of different types of errors, and all this data comes from all kinds of different places. The flash data is from Google. I've been talking before going to Google. I've worked with Google in the past. I had very good experiences. I would have been curious just to broaden my experiences, work with other companies. And I was in discussions with some, but it's really hard to find companies that, first of all, have a large number of machines, that collect really good data, and that are willing to publish about it. And then in the end, I was back at Google.
So you mentioned the Milky paper
yes.
from Intel.
Yes.
And actually, if you read like some of his work, he actually talks about why, if you look at kind of what we do in the lab,
yes.
worst case,
yes.
you expect that things will exponentially degrade.
Yes.
But when you look at a realistic case,
yes.
Where we're not continuously program erasing,
yes.
there's some workload dependency,
yeah.
you don't expect this exponential. So his work actually
for some of these
might
things
help explain what
yes, value factors, yeah. I mean, from what I remember about this paper, though, is that, and that might explain also the differences from the field and in research papers. I think the assumption that he makes is that there's a certain probability that bits will flip, and we just look at, depending on your ECC, what is the chance that more bits will be flipped than what your ECC can support. And it's kind of the assumption that things happen randomly. And I think what this data says is that basically real-world failures don't happen because random events, like random bit flips, just all happen at the same time, because that's what you can protect against relatively easy by doing this math. It's when you have correlated failures because there's some underlying cause, there's some problem in your hardware, and suddenly you have many more things fail simultaneously than you were thinking is likely if failures were uncorrelated. Any more questions? Yes.
I'm not sure what I'm asking or how to ask it, but I would think that different types of servers would have different types of read-write patterns. A Google machine that's the library that has everything archived.
Yes.
Could be doing read-onlys for hours at a time, and only doing an update occasionally after raw data.
And that is very true. So on these drives, all the drives from one generation, they have the same FTL, the same ECC, so they were not optimized for one particular application. They are used across all the different applications at Google, and those might look very different. So that's one reason why I can get some of these results, why I can get some drives that are very young and have a pretty high P-cycle count already, and some that are pretty old and still have a pretty low P-cycle count.
And I guess part of what I was wondering was whether within a company like Google, whether they isolate different servers to be performing different functions, or does every machine do a broad mix of everything that has to be done without trying to segregate?
No, different. So there are some clusters that are reserved for particular purposes, but I didn't have information about what was running in which cluster. I mean, I did have information about the workload in the sense that I had the counts of number of read operations, number of write operations, number of erase operations per day, but that's all the information I had. And the most common use actually for across all these workloads was as a caching layer, not so much as persistent permanent storage.
So any idea what will happen in the 3D structure?
I have no idea. So I have some data, and that's still not 3D. This is things that were put in production a few years ago. But that was basically the second and the third generation of drives. And although the ECC was changed and got stronger over time, error rates nevertheless got worse. So that doesn't look too good. But then I mean people also do different things internally and at the FTL, right? People are talking about, I don't know, using, for example, RAID across different flash chips. Who knows what people will come up with to counteract the decrease in individual flash cell reliability.
One thing you can do with caches and you can do with Google scale is you can sort of go through and do a refresh and read and run through and just re-image or whatever and change like the ECC after 6 months.
Yes. And that's one of the things that I was thinking about. So given that we're working on prediction, it looks like you can somewhat predict, maybe not simply on RBER or number of P cycles alone that you've seen. You can, taking other things into account, you can maybe predict. How do you use that? And one thing would be that you do some form of adaptive ECC. Yeah, that makes perfect sense.
Google scale, you can do it.
Yeah, they have control over everything. So
maybe that's what Google does. That's why they don't know what to tell you.
Why not just save everything in the cloud?
Can't say anything about
that. Put it in the cloud. What is that
cloud?
That clouds up all the problems. Yes.
So DRAM guys got good enough that they were counting, cosmic rays. Have the flash chips found anything like that?
So cosmic rays are one thing. So I've looked at DRAM reliability, and I did actually try to figure out whether cosmic rays are an issue or not. And they are probably affecting error rates, but not so much uncorrectable error rates. Because what I saw for DRAM as well is similar to what I'm seeing here. There was a very strong correlation between errors. So if you have a high number of errors on a DIMM, or even like on a particular address, it keeps repeating. And if it was cosmic rays, it's not very likely that the cosmic rays would always hit the exact same spot on the DRAM. Oh, excuse me.
Or it could also be a defective chip. Because the arrays are badly done.
Exactly, that's what we found. So that it might be bad cells. It might be like there was also row and column correlations.
Physics.
Exactly.
Partially broken.
Exactly. And one of the things that we did actually simulate is what if you, at the operating system level, given that there is this high repeatability of errors, what if you just at the operating system level at that point decided, so the page, the physical page that uses that part of the DRAM DIMM, the OS will just decide not to use it anymore. And you lose, whatever, 4K, whatever your page size is in memory, but that's pretty small compared to your overall memory. And that fixes a lot of the issues that you will have further down the road, actually. And we did a detailed simulation study of that.
Actually, personally, I'll bet you that if you analyze your infant mortality stories and correlate it with the physics, you can make much better predictions. It's basically a Poisson-like process versus, if you're taking averages, then you assume essentially Gaussian central limit theorem. That's very different.
Yes.
So anything that has to do with averages, you essentially average out a lot of the physics. That's why the models don't work.
That is true, and I mean, I can tell you lots of stories about averages and why averages are a problem. And one of the reasons averages are a problem is that there are clearly correlations. So some drives are bad, and they just get really bad. So I haven't made this a big point, but if you look at the labels on all my graphs, it was, for example, median RBER, median and not mean RBER. Because if you take means, you don't see any trends. It's so blurred by those individual points that are outliers in the spectrum to the degree that they dwarf everything else.
Also, that different means, by the way. Our president advocated at some point harmonic mean for performance prediction. And there's a very good math reason. There are other means too. So the standard mean, yes, it correlates with Gaussian in some sense, but that doesn't make any sense.
Yeah. Yeah.
Cool.
Okay.
Okay.
Thank you.
Thank you.